in previous lectures, so we have seen the differences between the scanning electron microscopy and transmission electron microscopy. So where these two types of microscopies have their own significant differences, right? So after the characterization of nanomaterials, after the fabrication of nanomaterials, so the characterization will be done by different characterization techniques like XRD, right? And we have the scanning electron microscopy and transmission electron microscopy, and we have seen individually what is scanning electron microscopy, what is transmission electron microscopy, and what are the advantages of using this, what is the advantage of using scanning electron microscopy, and what are the advantages of using transmission electron microscopy. So in today's lecture, so we will see some more characterization techniques. Already we have been we have acquainted with this type of techniques like AFM. AFM represents the atomic force microscopy, and MFM represents the magnetic force microscopy, right? So in today's lecture, we will see the differences, the basic differences between the atomic force microscopy and atomic force microscopy and magnetic force microscopy, right? So, first of all, let us see what is this atomic force microscopy, as we have seen already in our previous lecture. So, today we'll see some of the differences, what are the basic differences that we can synchronize between the atomic force microscopy and magnetic force microscopy. Of course, the magnetic force microscopy is used to characterize magnetic materials, whereas this AFM, that is atomic force microscopy, is basically an instrument which is used to characterize all the type of materials, irrespective of the domain, right? Irrespective of the domain, we can characterize irrespective of that particular domain, right? We can characterize any liquid material. We can go for any types of atomic force microscopy. But the main thing between the AFM and MFM is regarding the tip, a magnetic tip. So this tip plays an important role in this type of microscopies, right? So in that scenario, let us see what are the differences between the atomic force microscopy and magnetic force microscopy. So what is this atomic force microscopy? So the atomic microscopy is an instrument that can analyze and characterize the samples at very macroscopic level, right? At microscopic level, not microscopic. So that is what we can characterize samples at microscopic level. The atomic force microscopy is an instrument that can analyze and characterize samples at the microscopic level. This means we can look at surface characteristics. We can see the surface characteristic with very accurate resolution, right? So which is less than 1 micrometer, Right, so that is what atomic force microscopy is, an instrument that can analyze and characterize samples at the microscopic level. This means we can look at surface characteristics with very accurate resolution, which is less than 1 micrometer. So this is what the atomic force microscopy resembles. So this is what the instrument that we see, and this is what in the laboratory frame, and this is what some simulated material where the tip interacts with the metal surface, with the surface of the material, and we can see what type of image that can be obtained. So this is what the 3D image what we can see of atomic force microscopy. So atomic force microscopy is an instrument that can analyze and characterize samples at the microscopic level. That means we can look at surface characteristics with very accurate resolution, less than 1 micrometer. So the atomic force microscopy is being used of technologies affecting the electronics, telecommunications, biological, chemical and energy industries. Also, the AFM is being applied to studies of phenomena such as abrasion, adhesion, cleaning, corrosion, etching, friction, and polishing. So these are some of the phenomena. So those are some of the phenomena where the AFM being applied to study the phenomena such as the abrasion, right? So what is the abrasion material? So what is the adhesion? So how much material is touching that particular surface, right? So we call it as adhesive forces, right? And other is the cleaning. So the cleaning of the surface, and how much corrosion, corroded materials you can see. So how much corrosion is being done, and how much etching. Etching means how the sample is being projected upwards. So how much it is being etched, with what nanometers or what micrometers the material has been etched. Right, and friction, we can see the type of opposing forces, right? Opposing forces of friction, opposing force that is made on the surface of the material, right? And the other most is the polishing, right? So polishing is the thing, but we need to study the surface morphology, right? Surface morphology, smoothness of the material also can be studied by using this particular atomic force microscopy. Atomic force microscopy is that is why it is being used in used of technology affecting the electronics, telecommunications, biological, chemical and energy industries. So if you see some of the history of the AFM, So in the fall of 1985, the first AFM was made by Gerd Binning and Christopher Gerber, who used the cantilever to examine insulating surfaces. A small hook at the end of the cantilever was pressed against the surface while the sample was scanned beneath the tip. The force between tip and sample was measured by tracking the deflection of the cantilever. So this is what we can see, some of the history of the atomic force microscopy. So atomic force microscopy was first came into existence in the year 1985. So there is a small cantilever, that is a small tip-like cantilever which hits the surface. A small hook at the end of the cantilever was pressed against the surface while the sample was scanned beneath the tip. So the force between tip and sample was measured by tracking the deflection of the cantilever. So these are the different components of AFM, right? So we have the probe head, the laser on switch, and laser beam string screws. So XY transition screws. So XY transition is the resolution what we can see on the interface, right? At the same time, we have the laser intensity and position indicators, positive sensitive photodetectors, PSPD adjustment screws, and XY translation stages, and cartridge position screws. So these are some of the components of atomic force microscopy where we can study it, right? So what are the components of AFM? So AFM has the following components like piezo crystals, and probes. Piezo crystals are ceramic materials that expand or contract in the presence of voltage gradient, and conversely they develop an electrical potential in response to mechanical pressure. So in this way, the movements in X, Y and Z directions are possible. So that is what we have seen when we see about the frame, right? When we see about the frame, that is XY transition screws. So to screw that particular translations, so we go for some crystalline methods. We go from crystals. Like one of the crystals is a piezoelectric crystal. So these piezoelectric crystals are the ceramic materials that expand or contract in the presence of voltage gradient, and conversely they develop an electric potential in response to mechanical pressure. So in this way, movements along the three dimensions X, Y, Z directions are possible. So the next component, or very important component, is the probe. Right, so probe is usually touches the sample surface, right? So this probe is attached with some cantilever. So the cantilever is frequently adjusting the probe so that it can move on the surface of the material. So that's why the probe represents the micro machined cantilever with a sharp tip at one end, which is brought into interaction with the sample surface. So they are characterized by the force constant and resonant frequency. So when the cantilever adjusts, when the cantilever in interacting with the probe, probes on the sample surface, then the sample will vibrate, right? So there will be some vibrations. So due to these vibrations, they can calculate some physics, some wavelengths. Due to this vibration, they can calculate some parameters like frequency, amplitude, right, time period, and all. So these are some of the components of ASM. And the other is a beam deflection. So to detect the displacement of the cantilever, a laser is reflected off the back of the cantilever and collected in a photodiode. When the laser is displaced horizontally along the positions top BA and bottom DC, there exists bending due to the topography. While if this movement is vertically left BD and right AC, it produces a torsion due to friction, which is called the lateral force. So these are some of the components of AFM. So this is how the deflection takes place, right? So this is how the laser position detector, where it hits the cantilever. The cantilever will in turn interact with the probe, and we can see the detector along the control form, right? So this is what we can see, right? So how to work? A sharp tip is scanned over a surface with feedback mechanism that enables the piezoelectric scanners to maintain the tip at constant force or height. Tips are typically made from silicon 3 and 4 or silicon, right? AFM has an optical detection system in which the tip is attached to the underside of a reflective cantilever. A diode laser is focused onto the back of a reflective cantilever. The photodetector measures the difference between the upper and lower photodetector and then converts into the voltage, right? So there are different modes of AFM, right? So one is a contact mode and another is a non-contact mode. So in contact mode, in this mode, the tip makes soft physical contact with the surface of the sample. In contact force mode, the deflection of the cantilever is fixed and the motion of the scanner in Z direction is recorded. By using contact mode AFM, even atomic resolution images are obtained. Even the atomic images resolutions are obtained. So these are the working modes of AFM. So these have the advantages like high scan speeds, atomic resolution is possible, easier scanning of rough samples with extreme changes in vertical topography, right? And what the disadvantages? Lateral forces can distort the image. Lateral forces can distort the image. Capillary forces form a fluid layer, can cause large forces normal to the tip sample interaction. Combination of these forces reduce spatial resolution and cause damage to soft samples. Right. So these are some of the working modes of AFM and the advantages and disadvantages of using this particular atomic force microscopy. So as I told, the working modes of AFM, one is the contact mode, other is the non-contact mode. In this mode, the probe operates in the attractive force region and the tip sample interaction is minimized. The use of non-contact mode allowed scanning without influencing the shape of the sample by the tip sample forces. In most cases, the cantilever of choice for this mode is the one having high spring constant of 20 to 100 nanometers so that it does not stick to the sample surface at small amplitudes. So what are the working modes of AFM? So that means the advantages and disadvantages of non-contact mode. Low force is exerted on the sample surface and no damage is caused to soft samples. So whereas in case of disadvantages, lower lateral resolution limited by tip sample separation, slower scan speed to avoid contact with fluid layer, usually only applicable in extremely hydrophobic samples with a minimal fluid layer. So what are the working modes? In non-contact AFM, that is NCAFM, is one of the several vibrating cantilever techniques in which an AFM cantilever is vibrated near the surface of sample. The spacing between the tip and the sample for the non-contact AFM mode is of the order of lengths to hundreds of angstroms. This spacing is indicated on the van der Waals curve of a figure. This is what we represent. This is what we represent in non-contact AFM mode. And if you see the Coulomb interaction between the force, the atomic force and the interaction, the interatomic distance, we can find this type of variation for the non-contact modes. Right? So these are the repulsive forces, these are the attractive forces, right? So in a non-contact force, we have a non-attractive force, and in the upper part, in the repulsive force, we have in the indeterminate contact, in intermittent contact, we have the repulsive force, whereas in non-contact, we have the attractive forces. So working modes, see, because the force between the tip and the sample in the non-contact region is low, it is more difficult to measure than the force in the contact region, which can be several orders of magnitude greater. So in addition, cantilevers used for non-contact AFM must be stiffer than those contact with the sample surface, right? Right. So thus a sensitive AC detection scheme is used for non-contact AFM separation or AFM operation, right? In non-contact mode, the system vibrates a stiff cantilever near its resonant frequency, typically from hundreds to 400 Hz, with an amplitude of few tens of angstroms. Then it detects changes in the resonant frequency or vibration amplitude as the tip comes closer to the sample surface. The sensitivity of the detection scheme provides a sub-angstrom vertical resolution in the image with a contact AFM. So working modes of AFM are, these are the advantages and disadvantages. Higher lateral resolution 1 nanometer to 5 nanometer. Lower forces and less damage to soft samples in air, almost no lateral force. And disadvantages, slower scan speed than in contact mode. So these are the working modes of AFM, right? So these are what the images what we can see. Here, right? Whereas in case of magnetic force microscopy, so this magnetic force microscopy is based on the use of ferromagnetic tip as a local field sensor. So magnetic interaction between the tip and the surface results in a force acting on the tip, right, which can be detected from the deflection of the cantilever. Alternatively, the dynamic properties of the tip oscillation, that is amplitude, phase or frequency, can be used. In this case, the observed signal is proportional to the derivative of the force. The tip is scanned several tens or hundreds of nanometers above the sample, avoiding contact. Magnetic field gradients exert a force on the tip's magnetic moment, and monitoring the tip or cantilever response gives a magnetic force image. To enhance the sensitivity, most MFM instruments oscillate the cantilever near its resonant frequency with a piezoelectric element. Gradients in the magnetic forces on the tip shift the resonant frequency of the cantilever. Monitoring this shift or related changes in oscillation, amplitude or phase produces a magnetic force image. So what are the applications? The applications of MFM are, they can be used in magnet recording media, so that is what micromagnetism, domain wall dynamics, and pin failure analysis in electric circuit, studies of superconducting current. Right, so these are some of the applications where the MFM images can be used. So this is what the magnetic force microscopic tip interacting with the sample surface, right? Tipping interacting with the sample surface, and we have different spins, ferromagnetic spins in different directions. So MFM images spatial resolution of the magnetic forces on the sample surface, and the resolution is around approximately 10 to 25 nanometers. The system operates in non-contact mode. An image taken with the magnetic tip contains information about both the topography and the magnetic properties of the sample. Which effect dominates depends upon the distance of the tip from the surface, because the interatomic magnetic forces persist for greater tip to sample separations than for the van der Waals forces. If the tip is closer to the surface in the region where standard non-contact AFM is operated, the image will be predominantly topographic. As the separation between the tip and the sample increases, magnetic effects become apparent. Right. So a magnetizer is needed to magnetize the tip. Note that the structure of soft magnetic samples like permalloy or garnet films can be significantly changed by the field of the tip that has a relatively high coercivity. Tip reduction reorientation of surface magnetization and surface-induced reorientation of the tip magnetization can complicate the image interpretation. So this is how the image interpretation of the sample takes place, right? Lift mode, that is a MFM and EFM. Since magnetostatic, electrostatic force can be either attractive or repulsive, problems with feedback loop stability in the non-contact imaging modes are likely to occur. Cantilever measures surface topography on the first main scan. Cantilever ascends to lift scan height. Cantilever follows stored surface topography at the lift height above sample while responding to magnetic influences on second scan measured by amplitude, phase or frequency detection, right? So this is what the lift mode, that is for magnetic force microscopy and electric force microscopy. So this is what the tip of the image. So the tip, when interacting with the sample surface of a ferromagnetic sample, so we have the magnetic domains, and these are the flat magnetic sample. We can see a different path of, this is the path of the cantilever. We can see this is the path of the cantilever where it actually follows, right? So this is magnetic domains, flat magnetic sample, and this is the topography. And we can see the MFM image of that particular sample. We can see certain circular-like structures, right? So these all what represents the vortex states. Is what we can determine the vortex state, right? So circular. So these determine the vortex. So this means this is what the sample for magneto-optical disc, right? So magneto-optical disc, actually MFM images are characterized, and people also go for Kerr effect, right? So that also we can scan that images, right? So this is some of the physics behind that tip surface magnet, that is F equals to Q mu naught into Q plus M delta H. So if the length of the effective domain at the tip apex is small compared to the characteristic decay length of the sample stray fields and the surface fields, the tip can be approximated as a point dipole. We know that dipole is nothing but a set of two equal and opposite poles, right? So what is north pole, south pole? Whereas in electric poles, we can tell that a dipole is nothing but a set of equal and opposite charges separated by some fixed distance, right? So when it is separated by some fixed distance, then it will possess the magnetic dipole moment, the electric dipole moment. So this electric dipole moment is given by P equals to Q into 2L, right? So this is what we can see about the dipole moment in electric field, right? In this case, the gradient of the stray field in the vicinity of the surface rather than the field itself contributes to the force signal, that is COT. For larger domain size, only the front part of the domain effectively interacts with the surface stray fields. F equals to mu naught Q here, the field is detected. So here we use nickel iron tips. Right? So these are some of the cobalt tip and the nickel tips where we can see certain images of cobalt tip and nickel tip, and this is what the spectrum you can see. So if you go for the quantification of MFM images, is virtually possible because of the magnetic state of the tip, which is generally unknown. The magnetic state of the tip is generally unknown. The tip-induced reorientation of surface magnetization of a surface-induced reorientation of the tip magnetization can be minimized by optimal choice of the tip material, which is having high coercivity and largest magnetic anisotropy, and imaging it at appropriate tip surface separations. The latter, however, results in the loss of spatial resolutions. An alternate approach is the application of soft magnetic tips or super paramagnetic tips with large susceptibility, right? So the magnetic structure of such tip aligns parallel to the surface fields, and the tips are sensitive to the absolute value of the magnetic field. Therefore, the susceptibility with the volume of the tip is given by the relation F equals to half chi V delta B square, right? Where chi represents the magnetic susceptibility and V represents the volume, and of course B represents the magnetic field induction, right? Of course, this is a three-dimensional case. We represent it as delta, right? So, interpretation of the magnetic force image data upon homogeneous materials and current carrying devices can suffer from electrostatic contributions to surface or force gradient signal contrast, especially for conventional metal or metal coated tips. So these are some of the references what we have taken to understand the differences between differences between magnetic force microscopy and atomic force microscopy. Thanks for listening.
Like, share and subscribe. Hit the bell icon for more updates.